Hello class, welcome to this lesson on 8.1, hypothesis testing part 2. This is the second and final part for this lesson. All right, so our question is, what is the decision-making process for stating and testing statistical hypotheses? This is just the same question as it was in part 1. Ultimately, with these two parts, we want to address that question. So remember that we stated the goals in the previous lesson. So the goals are the same. But this time we want to focus on the last two parts. Choose between the one and two-tailed test, and then understand the steps and use the steps in the hypothesis testing process. So we're going to talk about more of those steps, which involves, there's going to be more things that you're going to have to be able to do for the hypothesis process, rather than just stating the hypotheses. All right, so this is the vocab. So we're going to talk about the hypothesis test, statistical hypothesis, null, alternative, type 1, type 2. We kind of already talked about that in the previous lesson. So what we want to focus on are the bottom half, level of significance, test statistic, p-value, left-tailed test, right-tailed test, and two-tailed test. So we'll be introducing those in this lesson. All right, so again, the main goal is to be able to describe the decision-making process for stating and testing hypotheses and go through that process. So we're going to actually go through that through each of those steps. So let's first review what we talked about in the last class. So in the last lesson, we talked about inferential statistics. We mentioned that the point of inferential statistics is to draw a conclusion about a population characteristic. We call that a parameter. So the point is to draw a conclusion about a parameter using what we call a statistic. A statistic is a sample characteristic. So one example of inferential statistics at work is what we're doing now, the hypothesis testing stuff. The goal of hypothesis testing is to test a claim about a population. And then more specifically, it's a process kind of like the scientific method. We kind of talked about that it's very similar to the scientific method in which you have an observation and then you want to make a hypothesis. Similarly, you have a statement or a claim that you want to prove, and then you make a hypothesis based off of that, a statistical hypothesis. And then you collect data in order to determine if there's enough evidence to reject or fail to reject the null hypothesis. Remember, the goal, the ultimate decision is, do we reject or fail to reject the null hypothesis? That's a key here. No matter which decision we make concerning the null hypothesis, whether we reject or fail to reject, there will always be a chance that our conclusion was incorrect, type 1 or a type 2 error. So recall that a type 1 error, you reject the null hypothesis when you shouldn't have, right? Because it was actually, true. All right, and I put true in quotes. And then for type 2 error, you fail to reject it when you should have rejected it because it's not really true. Okay, it's really false. Okay, so that's what a type 2 error is. All right, so first off, we're going to talk about the first learning goal, which is the for this lesson, which is the test directionality. So this determines the direction of our test. Okay, so so depending on the alternative hypothesis or the research hypothesis, there is a specific type of test that we must choose. There are three of them: left-tailed, right-tailed, and two-tailed. So the left-tailed test is when the alternative hypothesis has the less than symbol, right-tailed, greater than symbol, two-tailed, not equal to symbol. So those are our tests, and it's very easy to determine. So once you state your hypotheses, your alternative specifically, you look at the alternative, not the null. You look at the alternative hypothesis, and it'll tell you which direction you're going to use for your test. All right, so let's look at the first case. The alternative is less than the null. In that case, that will look something like this. Let's say you have the null is mu greater than or equal to some number, k, or mu is equal to some number. And then in this case, the alternative or the research hypothesis is less than some number. In that case, you're going to be using a left-tailed test because of this less than in the H1, okay? So left-tailed test looks like this. So if you're drawing a normal distribution, for example, then you have your curve and you're focusing on the left tail of that curve. That's why it's called a left-tailed test. Now this blue shaded region is called the p-value. The p-value, we'll talk about what that is in just a second. But just for now, just note that the area on the left is the p-value. It represents some kind of probability. It's the area under the curve, right? So it's some kind of probability. Now, this right here, this ZT, and I'll go ahead and zoom in on that for just a second right here so you can see. This is a ZT. This stands for Z-test. This is called a test statistic. We'll talk about what a test statistic is, but it's basically something that you calculate when you perform a hypothesis test based off of your sample, okay? And this is what you're going to actually compare to your null hypothesis. So you're going to calculate this, and then from that you get your p-value. And notice that it's on the left side of the tail because it's a left tail test. All right. So what happens if it's a right tail test? Well, it's going to look kind of like this. So you have h0 could be greater than or equal to, or it could just be equal to. And in this case, that the alternative has to be opposite, so it's going to be less than. I'm sorry, not less than, greater than. So let me change this real quick. Should be greater than. Apologize for that typo. Change that right away. So it's going to be greater than. So think of it as an arrow, right? The less than symbol is pointing to the left, so it's going to be a left tail test. The greater than symbol is pointing to the right, so it's going to be a right tail test. All right. So for the right tail test, notice again, similarly to what it was before, we have the p-value to the right on the right tail test. And then the z-test is obviously going to be on the right side as well. All right, so now let's look at the last one. The final one is the two-tail test. So how does that look like? So for the two-tailed test, notice that the h0 is equal to, but the h1 is not equal to. So if the h1 is not equal to, you're going to use a two-tailed test. This is how it looks like. You have the p-value on both sides of the tails, on both tails. Now here's the key that you want to be concerned with here. Because each tail has a p-value, that means that each tail has half of the p-value. So if the p-value was 5%, each tail would have 2.5%, okay? If the p-value was 10%, each tail would have 5%. So I want you to be careful with that. So basically the p-value is twice the area to the left tail, just looking at the left side, or twice the value on the right side. So if the right side was 5, p-value is 10. If the left side was 5, p-value would be 10. Okay, it's always twice on each, just looking at one individual tail, twice that value. Okay, so hopefully that, makes sense. I wanted to emphasize that. All right, so next thing we're going to talk about these test statistics. So what is this test statistic that we have here, the ZT? What is that? The test statistic is the statistic that you calculate when you do a hypothesis test. And it's the statistic that you compare with the parameter in the null hypothesis. So this is you take your sample, you do a calculation based off of that sample, that's going to be called the test statistic. Now that test statistic, you're going to compare that to the mu or the p or the sigma on the null hypothesis to see what that is. You want to see if they're significantly different from each other based on the test, okay? And that's what the test stat is for, to compare. All right, so let's go over real quick what the test stat looks like for each type of test, okay? So let's look at, if you're talking about proportions, remember the symbols. For the population parameter for proportion is p. So I want you to make sure that you're, just kind of review that. The population parameter for mean is lowercase mu. The population parameter for variance is lowercase sigma squared. All right, so I just want to make sure you remember that. The sample version of the proportion, or the sample statistic, is p hat. So when you look at p hat, that means sample proportion. For the sample mean, that's x bar. You guys may remember that. X bar is the sample mean. And then the sample variance is s squared. The sample standard deviation would just be s, but the sample variance is s squared. Now, what does the test statistic look like? Well, for the proportions, the test statistic is your z-score. You may remember with a z-score. We talked about that in the previous chapter 6. So we're going to be using that, eventually. So the z-score. The means, we also use the z-score, but we can also use something called a t-score, okay? So for the test statistic for means, it's going to be the z-score if the sample size is greater than or equal to 30. And for the t-score, which, don't be concerned with that right now. Just for now, just keep in the back of your head that we use a t-score when the n is less than 30. We'll talk about that in another lesson. And then for the variance, we use what we call chi-squared. Okay, this right here is the Greek letter chi. Okay, that's the Greek letter chi, not chi or chai, chi. That's how you pronounce it. So it's chi-squared. All right. Again, we won't talk about that until probably near the last section of the chapter for variance. All right, but just keep that in the back of your mind. That's what a test statistic looks like. So what is the p-value? That's that blue area that we looked at earlier. The p-value is the probability of getting a sample statistic that is extreme or more extreme than what was attained from the sample, assuming that the null hypothesis was true. So assuming that the null hypothesis is true, which is what we always assume, we find what is the probability of getting that sample mean or whatever you're looking for that is that value or more extreme. So what is the probability of getting that observation that is that extreme or more? That's what the p-value is. All right, so things to consider about the p-value. A small p-value is considered an unusual event. A small p-value indicates that we have more evidence to reject the null hypothesis. This is important. Small p-value means you can reject the null hypothesis. A small p-value means that we have a statistically significant result. So for example, if we're talking about weights, let's say the average weight of an American is 190 pounds. Average American male, let's say, 190 pounds. And you went ahead and took your sample, you took a sample of 100 Americans, you found the average weight, and you found that the weight was 170 pounds for your sample, right? So we need to figure out, well, that sample, that 170 pounds is going to help you calculate your test statistic. That's based off of your sample, right? The 190 pounds is is basically your null hypothesis value, right? So it's your null hypothesis. So it's equal to. So you want to compare those 190 pounds, 170 pounds. Are they statistically significantly different? We don't know until we calculate the test statistic and we find the p-value. So once we find the p-value, then that tells us, okay, those two are very significant, which means that we reject the null hypothesis. Okay, so a small p-value is a good thing if you're trying to reject the null hypothesis. So that means that basically a small p-value means that the result is definitely different and it could not be due to chance. So if you got a p-value of 0.1%, that means there's a 0.1% chance that you're going to get that observation if the null hypothesis is true, which is very small chance, which means you should reject the null hypothesis. All right, so let's go ahead. The last thing I want you to know is that when we do p-values, we compare them to the significance level, the level of significance, which we're going to talk about now. That's how we know whether a p-value is too small or too large, is based off of the comparison to the significance level. So the significance level is the probability of making a type 1 error, okay? This symbol is the Greek letter alpha. You guys may know the Greek letter alpha, but just in case. So we use alpha for the probability of type 1 error, also known as the level of significance. Now you get to decide the significance level when you perform the test. So you as the researcher will decide that. However, there are some common guidelines. Some common significance levels are 1%, 5%, or 10%. All right, you can use any other ones in between, but those are the most common ones. So how do we perform a hypothesis test? Let's go over those steps. So first step is to state and claim the hypothesis statements mathematically, which we talked about that in the previous lesson. The second step is to identify the significance level alpha. You get to figure that out, right? You get to make up your level of significance, 1%, 5%, 10%, or anything in between. All right. Third step, determine the test directionality and sketch the standardized distribution. So we're going to be looking at some examples of normal distributions. So our standardized distribution will be the standard normal distribution, okay, which is on the right here. So you go ahead and sketch it and test the direction, determine the test direction. Fourth step is to, oops, let me make sure I do this. The fourth step is to calculate the test statistic and mark it on your standardized distribution. So that's this diagram over here. So we determine we sketch, on the distribution, we find out what our test stat is, we calculate it based off of our sample, and then we mark it on our distribution. All right. And then the fifth step is to calculate the p-value, which again, you're going to label that p-value on your curve here. The sixth step is to make a decision. So how do we go about making a decision? Well, here's your decision tree. If the p-value, you're going to compare the p-value to your alpha, which is your significance level that you choose. If the p-value is less than alpha or equal to it, if your answer to that is yes, you're going to reject the null hypothesis. That means you have enough evidence. If the p-value is not less than alpha, it's actually greater than alpha, then that means you will fail to reject the null hypothesis. So greater than alpha, reject, or fail to reject. Less than or equal to alpha, reject. All right, so that's your decision for step 6. Step 7, which is the last step, is to write out your conclusion. So you're going to write a conclusion based off of the claim. This is key. The conclusion is based off of the claim, not the null hypothesis. The decision is based off of the null hypothesis, whether you reject it or fail to reject it, but the conclusion is based off of the claim. Decision, null hypothesis, conclusion, claim, okay? So step 7 is you're going to write a conclusion based off of the claim. So I went ahead and provided this chart for you. This will help you write your conclusions, okay? So if your decision was to reject the null hypothesis, right here, if your decision was to reject and your claim happened to be the null hypothesis, then you're going to be using this, this statement right here for your conclusion. There is enough evidence to reject the claim that ... If you rejected the null hypothesis and your claim belongs to your alternative hypothesis, then you're going to be using this statement right here. There is enough evidence to support the claim that ... If you fail to reject your null hypothesis and your claim belongs to your null hypothesis, then you're going to be using this statement right here. There is not enough evidence to reject the claim that ... And then the last one, if we fail to reject, but the claim belongs to your alternative, you would use this last statement. There is not enough evidence to support the claim that ... And then you proceed to write out what the claim is, whatever that claim is. Okay, so it helps to look at an example. So example 1, perform a hypothesis test for the situation. The proportion of high school students who text while driving is 78%. A researcher computes the test statistic and gets a value of 2.85. The researcher chooses a 5% significance level. Assume the data came from a normal distribution. All right, so first step, remember that the first step is to determine your hypothesis statements, right, and your claim. So here, our claim, let's go ahead and write our claim, is that the proportion means P, right, of high school students is 78%. So that means it's equal to 0.78. Make sure you convert that to a decimal. So that's your claim. Where does that claim belong to? Well, that's a statement of equality, so that belongs to the null. So our null is our claim, or our claim is our null. And now it says the researcher chooses a 5% significance level. It doesn't give you any information. If it doesn't give you any other information about what the researcher thinks, then you're just going to use the opposite. So now it doesn't say that the researcher thinks is greater than or less than, so we'll say not equal to. All right, that's our step 1. Step 2, select your alpha. Here in this case, they tell you that the researcher wants an alpha of 5%. So 0.05, that's my alpha. Okay, it says right here, 5% significance level. All right, step 3, determine the direction of the test. Remember, the directionality of the test is dependent on the alternative. Now, since this is not equal to, that means it's a two-tailed test. So the direction is two-tailed. All right, and therefore we're going to go ahead and make our, and it says assume a normal distribution, so that means we're drawing a bell curve. So we draw a bell curve, and then we know it's two-tailed. Step 4, determine your test statistic. They already tell you what that is. They tell you the test statistic is 2.85. So let's write that down, 2.85. Now, because it's a two-tailed test, that means we have 2.85 and negative 2.85. Okay, so that's key here. So we have 2.85 over here, and that's your z test. Well, you can call it z test, your test value. And then we have the negative version over here. And then we're going to shade our p-value, which is the, both tails. Okay, and that's, so this is going to be, both of these represent my p-value. All right, so they're both my p-value. All right, so now the next step is to find the p-value. How do we find the p-value? Well, we know that this is a z-score. So we can use the z-table to find the p-value. Okay, so we're going to use the z-table here. We're going to look up a z-score of negative 2.85. You can also look up a z-score of 2.85 and then subtract from 1. Okay, so let's look up a z-score of negative 2.85. Remember, the table gives you, by default, the area to the left. So because of that, I'm going to look up the 2.85 and I'm going to double it. Why am I going to double it? I'm going to double it because remember, a two-tailed test, you find one of the areas and you double it to get the p-value. The p-value is twice the area. So let's look at, we're going to look up negative 2.85. Let's see here, negative 2.85. So that looks like an area of 0.0022. So that's the area on the left side. That's also the area on the right side, right? So I'm going to label that. So this p-value, or this area is 0.0, what was it? 0.0022. Yeah, 2 zeros. 0.0022. But that also means that this area is also 0.0022. So our p-value is basically combining those two, which is why you have to double it, because you have two tails, you got to combine them both. Okay, so our p-value is 0.022 plus another 0.0022, or just double it. Okay, so our p-value is 0.0022 times 2, because you have two of them, you just add them, so you get 0.0044. That's my p-value. So my p-value is very small here, and that's how you determine the p-value with a normal distribution. All right, so let's look at step 6. Make a decision. How do we make a decision? So our decision here, do we fail to reject or reject? Well, you got to compare your p-value to your alpha, right? So p-value, is it less than or equal to alpha? Well, our p-value is 0.0044. Remember that our alpha is 0.05, 5% significance level. This is true. It is less than alpha. Therefore, if it's less than or equal to alpha, you reject. So our decision here is to reject H0. Okay, we reject. Last step, conclusion. What do we decide to do? So remember, use your statements from the chart that I provided you. Since we reject, that means there is enough evidence. So if you reject, that means there is enough evidence. So in this case, we would say there is enough evidence. Okay, otherwise we would say there is not enough evidence if we fail to reject. Okay, so there is enough evidence to, now what did our claim belong to? Well, we said our claim belonged to our null hypothesis. Therefore, the wording that we use here is we reject, okay? So that's the wording that we use there. So there is enough evidence to reject the claim that, and then what's our claim? Our claim is the researcher chooses a 5%, no, the claim is the proportion of high school students who text while driving is 78%. The proportion of students who text, ... I won't write the whole thing, but just write out that claim, just to save a little bit of time. All right, so let's look at the next example. Perform a hypothesis test for each situation. The mean life of iPhone batteries is less than 2 years. You decide to conduct a hypothesis test with a 1% significance level. You compute a test value of 1.53. Assume that it's normally distributed. So step 1, let's write out our claim. Our claim was that the mean life is less than 2 years. So mu is less than 2. Does that belong to null or alternative? Well, that's inequality, so it belongs to the alternative. Now, because we got our alternative, we do the opposite, and that will be our null. Our opposite is greater than or equal to. All right, there's our statements, and we know that the claim belongs to our H1. All right, let's move on to the next one. Step 2, our alpha, it says you want to use a 1% significance level, so 0.01. Next step, direction of the test. Since the alternative is less than, that means it's a left-tailed test. So we're going to go ahead and draw our bell curve, normal distribution. Test statistic, they said was 1.53. They call it a test value, same thing. And it's a left-tailed test. So that means that we're going to do 1.53, which is around here. Since it's a left-tailed test, we're going to shade to the left, right? So that means all of this is my p-value. That's all my p-value, that whole thing. All right, so step 5, p-value. So we need to use the z-chart to find the p-value. So we're going to look up for 1.53. So 1.53, so that's 0.9370. So let's go back to our guy. 0.9370. That's my p-value. All right. So now we're going to go ahead and do the next step, decision. We got to compare this to alpha, right? So in this case, this is greater than alpha. Alpha was 0.01. Remember, that was my alpha. That's greater than alpha. That means we fail to reject. So we fail to reject. All right, so then the next step here to do our conclusion, since we failed to reject, we're going to say there is not enough evidence, okay? So there is keyword not enough evidence. In this case, since the alternative was my claim, we're going to say support, okay? There's not enough evidence we use the word support. Remember, if the claim is H0, you use reject. If the claim is H1, you use support. To support the claim that, and then what was our claim? Go back to our claim, that the mean life of iPhone batteries is less than 2 years. The mean life of iPhone batteries is less than 2 years. Okay. All right. So we're going to do one more example. This should be example 3, I guess, not example 2. So we'll do this one real quick and then we'll call it a day. So the proportion of teens that make more than $8.50 an hour is less than 29%. Someone wants to see if this holds up to the evidence. So she used simple random sampling. She wants to conduct a hypothesis test using a 10% significance. From the sample of teens, she computes a test value of 2.06, assume normal distribution. All right, so our claim, let's do our claim real quick. Proportion of teens is less than 29%. So proportion is P, so less than 0.29, less than 29%. That belongs to our H1. do the opposite to get the null. So it's be greater than or equal to. So let's go to step 2. Alpha, she says she wants to use a 10%, so 0.10. That last step here, the direction of the test. Since it's since the H1 is less than, we're going to use a left tail test. All right. So that means we're going to have to draw our bell curve, normal distribution. Our test stat, they said that the test stat is 2.06. So we're going to find it over here, 2.06. Let's see here. Oops, sorry. 2.06, and then we're going to shade the p-value. All right, so the test stat here is 2.06. There's a p-value. We need to find that, so we're going to use the z-chart. Remember, if you want to find the area to the right on the z-chart, you got to do 1 minus. If you want to find the area to the left, just look it up, which we only want the area to the left, so we look it up. So 2.06. 0, 1, 2, 3, 4, 5, 6. So this is 2.06. Oops, nope, that's 2.0. That's the wrong one. 2.06. So 0.9803. Is our area to the left. This is less than, this is greater than alpha. So because it's greater than alpha, we need to actually fail to reject here. So we're going to fail to reject. So I'm going to use FTR for fail to reject H0. Did I say fail to reject on the other one? Yeah, I did. So because we fail to reject, that means there is not enough evidence to, and now since the H1 was our claim, we say support the claim that ... I'm going to have you guys fill that out. That's just the claim that they mentioned in the problem. All right, we're going to cut it here because it's been about 30 minutes or so. Hope you took something from this lesson, guys, and stay safe out there. I'll see you in the next one.